Okay, welcome everybody. My name is Andrea. I work at Panacea Cooperative Research. Okay, so this talk concerns subject to camera distance estimation, which is basically what Sean also introduced, called focus distance, just two different terminologies. And well, this is a result of the work of 4 people: myself, Pilar, Enrique, and also Valentino Rulli. So a collaboration between Panacea Cooperative Research and also the Andalusian Research Institute in Data Science and Computational Intelligence. Maybe I can skip this because Sean already introduced it. We saw that the effect of the distance between the camera and the subject in pictures is called perspective distortion, and in short, it changes the appearance of the human face, and especially when you get closer to the camera, you're going to see effects such as your nose getting bigger and your ears disappear. And this effect is not linear; it doesn't correlate linearly with the distance. So it is especially relevant in the range up to well, you can see it's already below 2.5% after 5 meters. And it almost disappears after 12. So the closest distances are the most relevant. And of course, we want to know if 2 pictures are affected by different amounts of perspective distortion, because if we are carrying out any kind of comparison, we need to make sure that we are not seeing some facial traits that look very different. Despite being the same in 3D in the real world, when you look at them on a picture, they're gonna look different. So we need to know the amount of perspective distortion, and to know that we need to estimate the distance between the subject and the camera. That's the idea. And there are 2 existing methods to do that. One is based on the size of unknown object, which is the palpable feature size, and the other is a machine learning method based on deep learning, which is also being developed by somebody in the group. In this case, we had the idea of trying to use measurement taken on the face. We call them DPIs, which are dimension and proportionality indexes. And these are simply either measurement taken on the image or the ratio between them. Right? Okay, like in that case, I have highlighted 4 landmarks, and we can take the distances between them, and we also take the ratio among them. These come from, we chose these because of historical reason. Basically, they're not really special. And my intuition for the use of DPI was that if you check the relative sizes of my nose in these pictures, you can see that when you have a lot of perspective distortion, I can measure that my nose gets bigger compared to the distance between my eyes. So with just one of these indices, you can see that I get half the number. Okay, so that was the intuition behind the method. And of course, we want this to be an automatic method based on machine learning. So the idea is that we collect a lot of pictures, we place landmark on them, we measure those DPI, and then we hand it over to a machine learning algorithm to get us a model that can predict the distance to the camera. That was the idea. And a key point is that we would like to not to rely on knowing the focal distance, the focal length of the camera. That will be very useful because obviously you don't need to know one key parameter of the picture, but eventually we couldn't do it. So this work works by also knowing the focal length. And to collect all those pictures, we use simulated picture, having a 3D scanner especially designed for faces. We acquire a number of 3D models from volunteer, and we simulated picture basically. And we use this kind of setup. We consider for different camera or for focal lengths. And we moved our virtual camera in the range between 80 centimeter and 6 meters. And we also rotated the subject so that we could simulate many kind of facial poses. So in total, it was our data set is composed of 157 feminine and masculine subjects, and we simulated almost 50,000 pictures by varying the resolution, rotation in all the axes, and 4 different focal lengths. This is the set of DPIs that we use that are used historically in photon anthropometry. But of course, you have the issue that not all the landmarks they are based on are always visible. This could be due to occlusion, but even to the facial pose itself, because for instance, in lateral photo, you don't see half of the face. So we needed to use a machine learning system that admitted missing values, basically. And those are our results. We tested a number of models and eventually settled on gradient boosting being the one with the better performance. And we computed what the mean average error and also the relative error, and also the distortion with the formula I showed you before. And if we compare with the 2 other existing methods, we can see that compared with Perspective X, we have significantly better result. Our error is in the range of 5 centimeters, and there was around 30. And another advantage is that our set of facial poses is wider. And if we compare against our deep learning method, we get competitive results. We are slightly worse. One of the advantages is that our model is much more interpretable. We know we can check what DPIs are actually being used, and our formula, let's say, is much simpler. And another drawbacks of this other method is that they needed to learn to train a machine learning method for each focal distance, while in our case is the same model for all focal distances. And that's it. So I'll say that we definitely proved that DPIs are useful in estimating the distance, and we were able to find a model that is also robust to missing landmarks, which was a key advantage. And interpretability is also a key feature. And our future work is going to involve variability in the expressions, because we use only model with a neutral phase, and also taking into account the subjectivity in landmark localization, and also validating our real photographs. That's it. Thank you.